Hi, welcome to R2E. And today, uh, this is problem number 4 from Hand and Finch, and we will be solving it. And what the problem says, the title of the problem is Motion Along a Spiral. And what the problem says is that a particle of mass m moves in a gravitational field. So you have a particle moving like something like this. I mean, not like this, definitely. Uh, Along a spiral that is z given as k theta. So probably you are going something like this. If you look at in one plane, I mean, definitely you will be like making something like this, and you're also moving along z, and yeah. And this r, your r is constant, where k is a constant, k is also a constant, and z is the vertical direction. Now what I need to do is I need to find the Hamiltonian um, as a function of z, that is my canonical coordinate, and p, that is my canonical momentum for the particle motion. Now, so yeah, I need to find and solve the Hamilton's equation of motion and show that then the limit z goes to 0, uh, my acceleration in the downward direction, in the z direction, or second derivative of the canonical coordinate, is actually minus g. So let's try to solve this problem. So the step one would be to write the Lagrangian. So Lagrangian is defined as T minus of V. My kinetic energy will be 1 by 2 mx dot squared, and x dot squared, as Landau beautifully puts it, will be nothing but dx whole square upon dt squared. So in cylindrical coordinates, my dx square will be uh, nothing but dr squared r d theta square, r square d theta square plus dz square. Now here, as r is constant, so dr will be 0. So dx square will be r d r square d theta square plus dz square. Now from above equation, where dz is k theta, okay, just first of all let's get the x dot square. That will be r not theta, r theta dot r square, theta dot square plus z dot square. Now z is equals to k theta, and we want to find the Hamiltonian as a function of z and p. So I should write the Lagrangian as a function of z. Since there is only one variable out there where r is constant, theta can be written in terms of z, or z can be written in terms of theta. So there is only one independent coordinate as such. All right. So yeah, so z equals to k theta. So theta will be nothing but z by k. So this implies my kinetic energy would be 1 by 2 m r square z dot square by k squared plus z dot square. This will be 1 by 2 m 1 plus r square by k square z dot square. All right. So, and as far as my potential is concerned, my potential is definitely minus of mgz. So my Lagrangian will be 1 by 2 m 1 plus r square divided by k squared z dot squared plus mgz. And this is my Lagrangian. So my Hamiltonian will be minus of plus p z dot minus of Lagrangian. Now let's try to get our p. That will be del L upon del Z dot. That will be M 1 plus R square by K square Z dot. So my momentum, so like let's do the substitution here. So this will be M 1 plus R square by K square Z dot squared minus of 1 by 2 M 1 plus r square by k square z dot square plus z. All right, my handwriting is a little worse, but I hope it's still legible. Anyways, so yeah, so this is the Hamiltonian. All right, so the Hamiltonian is given as like this. Now let's try to get the, okay, so not yet exactly. So this will be 1 by 2 m 1 plus r square by k square z dot square plus gz. Now let's try to replace it by momentum. So we will have this employs. So my momentum is this. So definitely, yeah. So this whole equation, by using this equation of here and using it here, my Hamiltonian will become p square upon 2 m 1 plus r square upon a square plus mgz. All right. So we got the Hamiltonian. Now let us try to find the equation of motion. So okay, so for equation of motions, we have the first equation as a minus of pz dot, that is del h upon del z. This is equals to mg, will be just mg. All right, and I have z dot is equals to uh, p upon m 1 plus r square upon phase 2. Now this implies that z double dot will be p dot upon m 1 plus r square by this, now which is equals to uh, minus of mg m 1 plus r square by this. So m and m cancels, that will be minus of g on 1 plus r square by this. Now for r goes to 0, we have z double dot is equal to minus of g. So this is the same result that we wanted to prove in the limit, that r goes to 0, z is equals to minus of g, and we have arrived at. So thank you for watching this video. See you in the next video on the series of classical mechanics.